Hi, so this will be a video about Hooke's law. So since Hooke's law is relatively simple, I don't want to spend much time on deriving it. I'm happy to go over that in office hours though. What I'm going to do instead is do a couple of practice problems. I think these are slightly easier than what you should expect on your exams, but either way, they should give you some good intuition for how to use Hooke's law. So without further ado, Hooke's law is he says, giving further ado, Hooke's law is the simplest example of a constitutive law, which is a relationship between stress and strain. And it's constitutive because it makes up the material. So materials are constituted of constitutive laws, and Hooke's law is for linear, isotropic, elastic materials. So the first thing I'm going to do, is a little practice problem, is you might have seen in the class notes that we have G, the shear modulus, is equal to E over 2 times 1 plus nu. And the good question is, where does that come from? So let's try it. So let's draw our favorite boxes. They're going to be small this time, though. So let's say that we have a box that's undergoing some shear strain. As I talked about in the previous video, okay. Tensorial shear strain is slightly different from the engineering shear strain. There we go. In particular, 2 times epsilon 1, 2 is equal to gamma 1, 2. So this is the actual angle that we're going to see in our tensors. So let's see what happens now. We want to try to rotate this by 45 degrees so that we can use this formula up here. So let's try drawing now this box. What this box is going to feel is a stress in this direction, sigma naught, and a compressive stress in this direction, sigma naught. So, and it's gonna end up stretching and becoming long and steady. Great. So what we want to do to try to understand this now is maybe draw our Morse circles. So we'll draw them for both stress and strain. So on the strain one, we have gamma over 2, which comes from this, as well as E, which I'll call E naught, and sigma naught. Actually, let's erase the knots. Where we do have the knots is right here. So this will be sigma naught and minus sigma naught, and this will be epsilon naught and minus epsilon naught. So let's draw the circles. Okay, so and let's call these up here, we'll call them tau, and this will be gamma over 2. So gamma naught over 2, tau naught. Am I missing anything? I think we're good. We'll call this sigma naught minus sigma naught, epsilon naught minus epsilon naught. Okay, I think I have all the preliminaries out of the way now. So what we're going to do is we're going to go up and grab our Hooke's law. So we're going to say, we only need one of the equations for this one. So let's say epsilon in the 1, 1 direction is equal to 1 over E times sigma naught minus nu of negative sigma naught, right? And so when we work this out, I'll just go ahead and replace this with an epsilon naught. It's going to end up being 1 over E times sigma naught times 1 plus nu. And that's all E naught. Right. So now if we look at the radius of the Morse circle, we can see that sigma naught is equal to tau naught, and epsilon naught is equal to gamma naught over 2. Right? So let's go ahead and plug those in. And I'll do this in blue now. So gamma naught over 2 is equal to 1 over E tau naught, 1 plus nu. Oh, why did I change colors? Why did I do that? 1 plus nu. Finally now, if we rearrange, we get the thing that we wanted. So let me double check that. So tau is equal to E over 2, 1 plus nu, gamma. So there we go. And if you remember from MA 15, that is the shear modulus right here. So there it is. We can do the same thing now for the volumetric, the bulk modulus. And so to do that, we have to do a little trick. So I'm going to go ahead and copy and paste this. Gonna go into the copy. Okay, I'll make it smaller too. So the trick here is we're going to just go ahead and add all of these up. So epsilon xx plus epsilon yy plus epsilon zz is equal to 1 over e times 1 minus 2 nu of sigma xx plus sigma yy plus sigma zz. Great. And so if you remember from class, one of the things we did was we said that this is the volumetric strain, so the change in volume over the initial volume, and this is the hydrostatic pressure. Technically, it's 1/3 of the hydrostatic pressure. Right? So when we plug all those in now, we get the 1/3 p. And then I'll put in a 3, so that'll be equal to the E over 3, 1 minus 2 nu, times delta V over V naught. So this is now our bulk modulus. So that's where that comes from. And now this last one is, what does this tell us about the range of nu? So remember, we have these two things. We have E over 3, 1 minus 2 nu from the bulk. And we have up here E over 2 times 1 plus nu from the shear. And we know that the bulk modulus and the shear modulus both have to be positive. And so this one tells us that V needs to be less than or equal to 0.5. And this one says that V is greater than or equal to -1. Can it be? Yeah. So -1 is less than nu is less than 0.5. So these are where the ranges on nu come from. And one of the things you can think about intuitively, especially for the 0.5 one, is that when nu is equal to 0.5, this goes, it blows up, it goes to infinity. And so that's an incompressible material. It's a material that has an infinite bulk modulus, and no matter how much you press on it, it won't change volume. The shear one is a little bit more interesting. When you have a negative shear modulus, that's called an oxidic material, and they're usually made out of like kind of 3D printing special shapes like honeycombs and things like that. Like for example, if you had like a little mesh thingy like that you kind of pulled on. Oh, I gotta. This is a sidebar. Feel free to just end it now and go on. But I think it would be like this. Oh, I gotta erase this and sort of pack it in. So when you pull on this in this direction, it'll unfold in that direction. And so that's how they build these oxidic materials that have negative Poisson's ratio. So yeah, there we go.